Welcome back. We are doing part 2 of 2 on improper integrals. Last time I did a whole lot about the theoretical side of things, and I started doing some problem solving, but this time it's pretty much all problem solving of improper integrals. So that is my plan. Now, what we did last time, I'm going to do just a little bit of review of the review, as it were. We had a few tests. I need to remind you what these integral tests are, because we're going to be using them today frequently. So one of our tests is a comparison test. And it had two flavors depending on whether you think your improper integral converges or whether you think it diverges. I'll tell you the divergence one first. So, again, I did all this last time, but this is just to summarize. And let me just precede this by saying only works for positive functions. I mean functions which are always positive, or at least near their problem spots will do. So, okay. If you have negative, if the function becomes negative at any point, you have to do something else, and I'm going to tell you what that is maybe the last half hour of the class. I'll be addressing that. So for the moment, let's just pretend everything's above the x-axis. If you think, and of course you might be wrong, but if your intuition is that of this improper integral here, where you have a problem spot at either A or B, but not both and not in between. Last time I also discussed how to split up the integral so that you isolate the problem spots in different improper integrals. So if you think that this diverges, meaning infinity in this case, you cannot have oscillations because everything is positive. So the only way it could diverge is up to infinity in this case, since f is positive. So if you think that it diverges, you try to find something smaller, a smaller function, whose integral also diverges. Because then the smaller one is already infinite, and the bigger one is propped up underneath it. So try to find a simple function, or a simpler function. See, f could be really nasty. So try to find a nicer function, g, such that, and I should say g has to be positive in the sense that g of x should always be greater than or equal to 0. Try to find a nicer function g such that the integral of g diverges. So you're comparing it to g. Then the idea is the integral that you want, which is hard to deal with, is bigger than or equal to the integral, the new integral, which this should be easier to deal with if you've picked g properly. But that's already infinite because we've assumed it's diverging, and that's the only possibility when g is positive. So, i.e., this diverges as planned, as we hoped. Well, as you hoped. And that is the comparison test. And in order to justify writing this inequality, since both things are infinite and these are improper integrals, you need to use the words comparison test next to it. So put comparison test in order to really justify that is meaningful. Okay, so, of course, maybe you were wrong. Maybe it doesn't diverge. Well, if it doesn't diverge, if in fact it converges, then there's no way you can find such a function, and your search will be in vain. Luckily, I'm going to give you some sense, very soon, a sense of how to look for this function g. So for the moment, I'm not telling you. Soon I will. By the way, if you get the inequality wrong, or if this g actually converges, you're in what I call the whoop-de-doo case, meaning that you can maybe get some information, but it's not particularly useful. For example, if you know that a quantity is less than or equal to infinity, I tell you, A is less than or equal to infinity. What do you know about A? Nothing. It could be equal to infinity, or it could be less. So if I burst in through the room with the fantastic news, hey, I found that A is less than or equal to infinity, your response is, of course, whoop-de-doo, I already knew that. Everything's less than or equal to infinity. Tells me nothing. Okay, so that's what I mean when I say whoop-de-doo case. Now, let me tell you the other version. If you think that the integral actually converges, and I'm going to write this as CVG for the rest of the evening. If you think that this converges, try to find a nicer function. G, such that G is bigger than F. So this time you want G to be bigger than F and still to converge, such that, oh hell, did I miss something? I did. I left out the crucial thing here. I said it, but I left it out. G of x has to be smaller than F. Let's write it like f of x is bigger than G. So, sorry about that. You've got to fill that in. That and the other condition. So you want a smaller function whose integral diverges in this first case. Right? I said it, but I didn't write it. So G has to prop up f and also have an infinite integral. In this case, G of x had better be bigger than f. And the integral of G converges. Then, the integral we want, f, is now less than or equal to the bigger integral G, since G is a bigger function. And that we know is finite. It converges. And again, you should use the words comparison test when you write down such a thing. I.e., this converges. So that converges as you hoped. As usual, the picture tells it all. In the first case, here's your nasty function f. And you want to know, let's say we go from a to b, you want to know if this integral here diverges. You think it diverges. What you do is you find a smaller function g, whose integral still is infinite. If that orange integral is infinite, then the white integral, or the white area, is even bigger. So you've forced it upwards to infinity by something that's already infinite. Whereas if G, if you want it to converge, you better find something bigger. The blue function now, if that area is actually finite, then the white area is also finite. So you see it matters whether G converges or diverges, but you've got to make sure that if G converges, then it's above F. Or if G diverges, it's below F. Otherwise, you're in one of these whoop-de-doo cases. Okay, so that's the comparison test. Let me quickly remind you about the limit comparison test, the p-test. So, limit comparison test, which I'll always call LCT, because I don't want to write out 3 words. Limit comparison test, if the integral from a to b of f of x has a problem spot, and remember, for our intents and purposes, a problem spot, and I wrote this last time, I'm just going to dictate it this time, a problem spot is basically a vertical asymptote, or the number infinity or minus infinity. Those are always problem spots, and vertical asymptotes are problem spots. There are other more exotic ones, but as far as we're concerned, those are the ones that are going to come up. So if this has a problem spot, which I'm going to write as PS, not postscriptum, problem spot, only at, say, the left endpoint, although this works equally well with the right endpoint, or infinity, or minus infinity. If that's true, try to find a simpler function, or a nicer function g, and here I'm going to insist that they're both positive. Again, f and g are both positive in this. Otherwise, you have to do something else, and as I said, I'll tell you what that is later. So you try to find a nicer function g such that f behaves like g. So f has to behave like g, or be asymptotic to, twiddle, g, as x goes to the problem spot. A only needs to be from above. I need to remind you what this means. This means that the limit of the ratio of the two is 1. F over g is approximately 1. The functions are very close. Sorry, a question?
How do you prove that?
Well, that's a good question. I'm going to show you by example how to do these sorts of things very, very soon. I did some at the end last time, but just bear with me and you'll see. You will see. Okay, so if you can do this, I haven't really told you how to find the g in any of the cases yet, but this will all become clear very soon, I hope. If you can do this, then you don't even need two versions like you do with the comparison test. There's only one version. And you don't need to know what's going on in terms of convergence or divergence. You can say that this and the new one, which is hopefully easier, either both converge or both diverge. Colloquially, the one we want does what the one we just plucked out of the air does. So if you've reduced the situation from a nasty case to an easy case, and that's the idea. Again, I will give you some scope of how to choose the G. In fact, the last test that I'm going to go over right now is the p-test, and that basically tells you that we're almost all the time going to choose g of x to be 1 over x to the p. No matter what our function is, we're going to have to choose g of x is 1 over x to the p, but you have to be clever about selecting which p. And the p-test tells you about these new integrals of g. So in particular, just to remind you what it says, the problem spot at 0, if the problem spot is at 0, actually I did the infinity case first, just to be consistent with what I did last time. If it goes from a to infinity, so the problem spot here is at infinity, you need to know that this diverges if p is less than or equal to 1, but converges if p is greater than 1. But if the problem spot is at 0, the opposite is the case. Here the problem spot is at 0 because 1 over x to the p has a vertical asymptote there. This diverges now if p is greater than or equal to 1, and converges if p is less than 1. I forgot to say one thing about the limit comparison test, and it's to do with g. And I should have said where g only has a problem spot at x equals a. You don't introduce any new problem spots. I said it last time, I just forgot to mention it. I should also mention that if the problem spot is at b instead, then everything is the same except that this becomes a left-hand limit at b. So you might wish to just sort of mentally replace it by x goes to b minus if the problem spot is at b instead of a. So not really any difference between the left and the right. Okay, so guess what? With these three tools, we can solve a whole lot of problems. Not every problem, because we still have to worry about negatives, but we can pretty much solve every improper integral problem apart from that will come up at least in this course. We just have to use them properly. And to do this, I embarked and I continue to go along that journey, a study, an analysis of how certain functions behave. And I'm going to start off, as I did last time, with behavior of certain functions at infinity. Now, I already spent a lot of time last time on polynomials. So I'm just going to summarize this and remind you that if an x to the n is the highest degree term in some polynomial, where this is a polynomial, then p of x twiddles its highest degree term as x goes to infinity. We've seen this time and time again. The largest term dominates, so highest power dominates at infinity. In a poly. Okay, I did a few examples last time. I'm going to do one really, really quickly this time, just to show you what's going on, but I've left my pages on the other side. All right. So let's just take a look at this. Suppose you have the integral from 8 to infinity, 1 over 2x cubed minus 3x to the point 1. Now, actually, the denominator is not even a polynomial. It's a polytype function. You see, this power of 0.1 was supposed to be an integer, but it's not. Doesn't matter. X to the 3 is still a higher power than x to the point 1. So this should dominate. The only question is, do we think that there are any problem spots other than infinity? Whenever you look at an improper integral, you've got to ask, where are the problem spots first? And I look at this and I say, look, infinity is always a problem spot. So certainly that's the case. But maybe the bottom could be 0 at a certain point. Still, 2x cubed is pretty big when x is bigger than 8. Much bigger than 3x to the point 1. So the bottom is always positive. There's no problem spots. If you start getting close to x equals 0 or something, well, there would be a problem spot. So the only problem spot actually in this integral is at infinity. So I whip out this principle and I say, well, 2x cubed minus 3x to the point 1 should behave like 2x cubed as x goes to infinity. I'm ignoring this lower power here. Now, that's probably worth proving, and it's not very difficult. You see, here's the justification of this. If you want to show something like this, then you just consider the ratio. In this case, as x goes to infinity, you have 2x cubed minus 3x to the point 1 over 2x cubed. You see, if you're going to write something behaves like something else, write down their fraction and take the limit. And in this case, it's pretty straightforward. This equals the limit as x goes to infinity of 1 minus 3 halves, and I think you have 2.9 on the bottom. 1 minus 3 over 2x to the 2.9. The constant's 3, 2, nothing matters. It's just that as x goes to infinity, this whole term goes to 0. And so that limit is 1. And if the limit of the ratio is 1, the two functions twiddle each other as x goes to whatever it is, and in this case, infinity. All right. How about that? So what? We don't have 2x cubed minus 3. We have 3x to the point 1. We have the reciprocal of that. Well, as I discussed last time, you can take powers of both sides. You can't add them or subtract them. You're not allowed to subtract 2x cubed from both sides. That's a load of bull. But you can multiply, you can divide, and you can take powers. In this case, what I want to do is take a reciprocal, which is a minus 1 power, and it's also true that 1 over 2x cubed minus 3x to the point 1 behaves like 1 over 2x cubed as x goes to infinity. If you like, you could just start with that and consider the ratio of this to this. Works out 2. You get 1. Anyway, the point of all these shenanigans is that instead of writing equals or greater than, I just stop. Whenever I'm going to use the limit comparison test, I just stop. By the way, I'm using the limit comparison test because I've got twiddles. Twiddles means LCT. Don't try to explain to anyone not doing calculus what that sentence means. Twiddles means LCT. There you go. Okay, so anyway, consider, here's how you set it out. First of all, you've got to do all that stuff. Now consider this new integral, the integral from 8 to infinity, just 1 over 2x cubed. After all, the integrand we care about behaves like 1 over 2x cubed, at least near the problem spot. Well, does this converge or diverge? First of all, we can pull out the 1/2 because it's just a constant. Constants don't matter. So I integrate from 8 to infinity 1 over x cubed dx. Converge or diverge? How do we know? P-test. 1 over x cubed. Look it up over here while we still have it. We're in the infinity case. 1 over x to the p. P is 3. 3 is bigger than 1, so according to this, it converges. So you say this converges by the p-test. Well, that's all we need. This does the same thing. Our original integral does the same thing as this. So therefore, and you rewrite the original integral, converges as well by the limit comparison test. But you do need this statement that, unfortunately, is a little bit squashed down there, but that statement is what you need. And you have to justify it somehow. So every limit comparison test problem is going to be something like this. We're going to take our original integrand, that's what you get when you ignore the integral and the dx, and we're going to say it twiddles something. And hopefully the something is just 1 over x to the p, or a constant multiple of it. The half doesn't matter. And then you're going to look at that, and you're going to see whether it converges or diverges using the p-test. And then you're going to claim that the original thing, the original integral, does the same thing by the LCT. That is the template for all these solutions. Notice how few actual equal signs are in the solution. It is so far removed from your typical calculate blah, and you go this equals this equals this equals this, done. No, here you have to write an argument. You have to. It's like a proof. It is a proof, actually. But you're using a test to do the dirty work, as it were. Limit comparison test has a lot of meat in it that is at your disposal. Or if you're a vegetarian, I guess it has a lot of soy or something. I don't know. What?
Can you give an example of two functions that behave like each other when x goes to 0?
I will, but I'm not going to do it just yet because I want to finish infinity first. You've got to do infinity before you can get to 0. Well, that's not true in general, but I thought it sounded nice. I will give examples. But if you really can't wait, Here's one. Well, even if you can't, here it is. Even if you can. That is true. After all, well, then you're going to have to wait. All will be revealed. But look, it works at 0 as well. Anyway, that's an aside. I'll be coming back to that. But it is sort of timely that we're looking at trig, because the next sort of function I want to look at is behavior of trig functions at infinity. And there's not that much to say. First of all, tan is a mess. It has asymptotes all over the place. But sine and cosine also don't have a lot of structure. They don't converge to anything. There's only really one useful fact that I can think of, and that is sine of anything is less than or equal to 1, as is cosine of anything. So it's less than or equal to 1 in absolute value. Well, what good does that allow? What good does that do you? It does allow you to solve certain problems, such as this. The integral from 8 to infinity. It's almost the same issue, the same problem. 1 over 2x cubed minus 3x to the point 1. But I am now going to add on sine of 100x to the 200 dx. So it's very, very similar to the other problem. So the question is, how different is it to add on the sine? What is the highest degree term? It is not 100x to the 200, even though this is a huge, huge number in comparison with the other two when x is large. The fact that you're taking sine of it reduces it to a number between minus 1 and 1. So imagine plugging in 8. 2x cubed is 2 times 8 cubed. That's already pretty big. 8 to the point 1 is not big. And sine of anything is between minus 1 and 1. So the dominant term is still going to be 2x cubed. So in fact, the modification to what we had before is that sine and cosine, or sine or cosine, are dominated, i.e. count as a lower power. Than, I'm not expressing myself very well, dominated by, i.e. count as a lower power than any positive power of x. So in the hierarchy, here we have x cubed. That beats up on x to the point 1, because 3 is bigger than 0.1. But even this would beat up on sine, because this still gets, well, never mind the minus, x to the point 1 still gets quite big. As x gets large, it gets very big. Whereas this is still trapped between minus 1 and 1 and is insignificant. So anyway, the point is, you just repeat the last problem. In fact, you repeat the last solution. Solution is identical to previous one, except I'm not going to write out the full solution in order to save time. That's up to you, but let's just say how we modify it. What we really want is that 2x cubed minus 3x to the point 1 plus sine 100x to the 200. We still want that to twiddle 2x cubed, and we better prove it. It's a little more complicated than last time, but not much. See, here's the proof. Limit as x goes to infinity. I should have said here as x goes to infinity. Whenever you write a twiddle, you have to say as x goes to something. So the limit as x goes to infinity of the ratio, this time we have a sine 100x to the 200, and we divide this by 2x cubed. So this time we get 3 terms. First one is 1. The second is 3 over 2x to the 2.9 as it was before. But now we have an extra term. So what is this limit? Well, as before, this goes to 1. that still goes to 0 because of the x on the bottom. How about this baby here? It goes to 0, but it's not as obvious. How do we know it goes to 0? Well, sine is between minus 1 and 1, but what principle are we going to use from way back in Math 103? Sandwich or squeeze. Yes, you have to know that again. I'm sorry. You have to know all of Math 103, almost without exception. Not everything, but you have to know maybe 70% of Math 103, and I'm not telling you 70%. So there you go. It is 0, and it deserves a separate proof. You see, sine of anything is between minus 1 and 1. So in fact, if you divide by 2x cubed, and because this is just review of stuff we've done before, the point is as x goes to infinity, that goes to 0, that goes to 0 as x goes to infinity. So you have to burble on about the sandwich principle or the squeeze principle to justify that this, in fact, does go to 0. And that is not acceptable as an answer. You have to write a few sentences. I am just saving some time here. But
if you don't have any positive powers of x?
If you don't have any positive powers of x, then you're in trouble. You could be in trouble. And actually, that is a very tricky situation. Let me give you one example of this. So I will actually answer that in 1 second. I just want to finish this problem. It's basically done. I leave it to you to finish it off. I mean, after all, this is twiddling the same thing, so the rest of the solution is going to be the same as before, and this integral converges. The sine term doesn't make much of a difference. So okay, are there any questions about that particular problem? Yes?
Is it always going to be like that? Obviously, we're going to have to write it out and prove it, but basically it's always going to be that.
You know, it's very hard in math to say anything is always going to be like that. You know, when you have a polynomial plus a sine or a cosine, right, unless the polynomial is a constant, which is what this gentleman's question was, you know, what if it's just 1 plus cosine or something like that? Basically, if there's any power of x that is not just x to the 0, so any power of x plus a sine of anything or a cosine of anything, and the problem spot is at infinity, then yes, this is always going to be like this. But, you know, there's so many different varieties. My only goal for this 2 hours is to show you as complete a selection as I can. But there's always going to be exceptions to anything. So most of the time, yes, this sort of question applies. Now, your question was, what if you don't have a positive power of x? And the simplest example of such a thing, well, a negative power is a problem, right? So a negative power of x on the bottom, I would say if you're going to have that, like if it was a 1 over x or something plus a sine, maybe take a common denominator, multiply through by x, and try to solve it. But these things can be quite nasty. Just consider a simple example like this. The integral of cosine x. There's no positive power at all of x. It's just cosine. Well, to do this, I'm afraid you can't use any of the tests. You have to bust out the definition that we did last time. It's the limit from 0 to n of cosine x. After all, n goes to infinity. You can see that that's going to look something like this. In fact, that's the definition of this. So we just integrate cosine. The integral is sine. So it's the limit, as n goes to infinity, of sine n minus sine 0. Sine of 0 is 0. So the question is, what happens to the quantity sine n as n goes to infinity? Does it have a limit? No. Sine n just oscillates between minus 1 and 1. This limit does not exist. Oscillates. So I'm afraid that for the more exotic examples where you have constants, but you do not have, for example, any powers of x added on, a lot of the time the answer is does not exist because of oscillation, but they can be extremely tricky to untangle. Extremely tricky. The same as if you have other powers of x which happen to be, say, negative. These things are often well beyond this course. In fact, you might say that I spent 5 years doing a PhD trying to understand effectively one improper integral and to see whether it converged or diverged. converged. Yes, it converged, but it was not easy to show that. It took about 100 pages of math to show that it converged. And when I was finished, I was so exhausted I couldn't remember why I cared about the integral in the first place. No, that's not true. I remembered. It was to get a math PhD. No, it was a useful integral. Anyway, so that seems to have occupied some time while I erased the board. Let me show you one other slightly different example that doesn't involve the sandwich principle. But suppose you look at just something like the absolute value of sine x over x squared. Everything's positive. I'm not doing negative stuff yet. I've taken absolute values because otherwise the numerator could be negative. So I have the absolute value of sine x over x squared. So there's no sandwich principle here. I could care less that this goes to 0 because I'm not trying to do an asymptotic sort of stuff. In fact, it would be wrong to say, oh, sine x behaves like 1. I've never told you this. This is wrong. I never told you this. The only thing I've told you about sine x when x is large is an inequality. So in this particular case, sine x is less than or equal to 1 in absolute value. That's true. So we can divide both sides by x squared. And now we don't have a twiddle. We have an inequality. So this suggests using the comparison rather than the limit comparison. So if you have a twiddle, limit comparison. If you have an inequality, try for comparison. So in this case, since the only thing we know about absolute value of sine x as x is large is essentially that it's less than or equal to 1, it doesn't go anywhere, it just oscillates back and forth. So our best hope is to do a comparison with 1 over x. And we better hope that converges, because otherwise we'll be in the whoop-de-doo case. Well, guess what? It does converge. Converges by the p-test, since p is 2, which is bigger than 1. So this is less than or equal to something which is less than infinity. This is a finite, nice number. Whatever it is, it doesn't matter. It's a nice number like 2. 1. I don't know what it is. This is less than or equal to it. Therefore, this converges by the comparison test. Not much to write there. It's a very simple problem. But again, it relies on your knowing what to do with trig functions at the problem spot of infinity. That's the only problem spot. If the integral went from 0 to infinity, you'd have a problem spot at 0 as well. But in this case, you don't. How would you do that? You'd have to split it up into 2 parts, from 0 to 1 and from 1 to infinity. Now, for the 0 to 1 part, I'm not ready to talk about it because then I have to talk about how sine behaves at 0, which is quite different. But we'll get to it. Okay, so that's all I want to say about trig. Now I have to tell you about exponentials. So, 3. How to deal with exponentials at infinity. Exps at infinity. And exponentials are normally e to the x in these types of problems. They seem to come up. But, of course, it could be any power. 2 to the x, 5 to the x, whatever. So here is the principle. We knew that the limit, as x goes to infinity, of any power of x over e to the x is 0. We've seen this before. You can actually use L'Hopital's rule n times. Every time you hit this with a derivative, this goes down a power, but this remains unscathed. So eventually you get 0. So this is true. The way we said it is exponentials dominate polynomials. Exponentials are bigger than polynomials, or powers of x. Exponentials grow quickly, i.e., another way of saying it is exps grow quickly at infinity. They're really fast. Exponential growth. It's faster than polynomial growth. Okay, this means that if you draw the graph of this function, x to the n over e to the x, it has a horizontal asymptote here at 0. It also, when x equals 0, it's at 0. So, and it's always positive, because remember, exponentials are always positive. E to the anything is positive. Please remember that. Write it down on your hand or something. I don't know. Exponentials are positive. I'm sure everyone will be impressed if you walk around with that on display. Now, the point is that this function has to do this, so guess what? I don't know what it does. It can't get too high, though. It's got to go up and then down because of this. So there's some c that it's less than. So x to the n over e to the x has to be less than or equal to a c. And then all I do is divide by x to the n, and I get my really useful principle, which you might as well just learn. E to the minus x, that's the same as 1 over e to the x, is less than or equal to a constant over x to the n. And this is true for any n. Doesn't matter what n is, as long, even if it's large, even very large. Okay, you can just remember this, but understand what it means. It's basically exponentials grow quickly, but if an exponential grows quickly, then its reciprocal goes to 0 very fast. So e to the minus x, if you drew a graph, it goes to 0 as x goes to infinity. It doesn't actually touch 0. But it goes faster than 1 over x, or 1 over x squared, or 1 over x cubed. You just need that constant in there because it's not quite true with c equals 1. This you may quote, and it's a really, really useful principle. So let me show you a simple example of how to use it. This is not the only way to solve this problem, but it's just about the nicest in my opinion. Suppose we take the integral of x cubed e to the minus x. So what's our intuition here? First of all, this is never negative. And by the way, this might normally be written as x cubed. Well, it could be written as x cubed over e to the x. In which case, we can just re-express it as x cubed e to the minus x. So in this case, x cubed becomes huge. The only problem spot's at infinity. There's no asymptotes. X cubed becomes humongous. But e to the x becomes tiny. What happens when you multiply humongous with tiny? You get tiny, but only because exponentials bash up polynomials. They really pummel them down to insignificance. So how are we going to do this? We cannot write x cubed e to the minus x as asymptotic to e to the minus x. That's not true. If it were true, then you could multiply both sides. Well, this would be as x goes to infinity. But since you could multiply both sides by e to the x, and you would get x cubed twiddles 1. And that is not true. X cubed does not twiddle 1. X cubed does get big. It's just it gets swamped by e to the x. So you need to use this inequality. Now here's the secret. You need to pick a power that is big enough not only to swamp the 3, but to leave a negative power in its wake. So what I would suggest is to add 2 to this power. 3 plus 2 is 5. I am going to say that e to the minus x is less than or equal to some constant over x to the 5. You will see. I can now use just direct comparison since everything is positive. And I can replace the e to the x by something bigger than it, which is c over x to the 5. Now the constant, it has to be there, but it's insignificant because constants don't affect anything. They just pop out of the integral. And in this case, having a power 2 more has cancelled out down to 1 over x squared. And that number 2 is bigger than 1. So by the p-test, it converges. So let's follow the logic. The original integral, however you choose to write it, is less than or equal to something which converges. Therefore, the original integral converges by the comparison test. Again, I'm using the comparison test. I don't have a twiddle. I have inequalities. So, comparison test. Now, the question is why 2? Well, you can see that no matter what this power was, 3, by picking 2 higher, 5, when it cancelled out, I was left with x squared. So even if this had been 3,000 and I chose 3,002, when I cancel them out, I'll still get x squared. Now, why not 1? Was that going to be your question? Okay, what if you did 1 more? So suppose mentally we'll just change this 5 to a 4. Then you would get, just instead of 1 over x squared, you'd get 1 over x to the 1. And now that integral 1 over x instead of the x squared diverges. And so you would be in the whoop-de-doo case. This is less than or equal to something that's infinite. It tells you nothing. So you actually could pick any number bigger than 4. You could do 4.0001 if you are feeling really stingy, because then you will get 1.0001 here, and it still converges. So you have to choose your number so that after everything cancels, you have a power bigger than 1, so that you can use the p-test effectively. A question? Okay, so the question is, I'm going to just ask 2 questions based on what you're saying here. One question is, does it matter if you pick something more than 2 bigger? So suppose I pick 500 or something like that. Well, that will end up with 497 there, and it still works. So you can always go bigger without hurting. So why not just always choose 500 or 5 million? Well, no matter what number you've decided you're always going to choose, I can just pick something larger and thwart you. You have to wait till you see what I throw at you before you choose the number. You've got to go after me to beat me by more than 2. So you cannot walk into this exam saying, I'm going to use 5 million whenever I do this, because then I will have guessed that you were going to use 5 million, and I will put 10 million there, and then you'll be screwed. Of course, I'm not omniscient, nor am I even making the midterm, nor have I seen the midterm. If you're watching on video, these guys in the room have a midterm tomorrow. Now, you can't see them on the video, but you can, I don't know if you can see reflections of angst emanating from the blackboard. That's not from the math, that's from the students in the room. So just thought I'd let you know. Okay, so all right, so what else do I have to say about exponentials? Not that much more. I thought I would do one more example. Well, one thing I do have to say is that the base of e doesn't really matter. It could be any positive or any power, any base rather, bigger than 1. So I just want to sort of comment that also works for 2 to the minus x, 3 to the minus x, etc. That inequality still works. For example, 2 to the minus x is less than or equal to some constant over x to the n, and you get to choose the power, and you can make it very large. Also, it doesn't even have to be x. It could be e to the minus x squared, or e to the minus p of x, where this is any polynomial, as long as the leading coefficient is positive. I don't want to write minus x squared and make it x squared. So it could be even e to the minus x to the 7 plus x to the 6 plus x squared. The point is that the leading coefficient is negative, so this is still less than or equal to c over x to the n. And there's a little bit of argument to say why that's true, but it's not so hard to see. All right, so inspired by this, I have one more problem, and it's going to involve a couple of the techniques that we've done so far. So here goes. The integral from 10 to infinity, x to the 1,000 plus x squared plus sine x, e to the minus x squared plus 6 dx. All right, so we have 2 factors. This factor is dominated by x to the 1,000, the highest degree term. We've already discussed that x squared is insignificant, and actually sine x is insignificant even compared to the x squared, let alone to the x to the 1,000. So the first thing to do is going to be to get rid of this. Now, this is not the only way to do this problem, but to my mind, well, I kind of want to just mentally replace it by x to the 1,000. So let's use the limit comparison test first. X to the 1,000 plus x squared plus sine x behaves like x to the 1,000 as x goes to infinity. And along the lines of your question from before, is it always like this? Yes. Here it is again. If you want to prove this, divide by x to the 1,000 and use the sandwich principle on this. So there's some justification, but it's exactly the same as we did before, except for slightly different numbers. So you've got to justify that. Remember, you take the limit of the ratio of this to this divided by this. Okay, so basically then, I'm going to say that the reciprocal of this also, well, continuing the working, the reciprocal, no, I don't need the reciprocal. There's no reciprocal. What I need to do is multiply both sides by e to the minus x squared over plus 6. So, x to the 1,000 plus x squared plus sine x times e to the minus x squared plus 6 twiddles just x to the 1,000 e to the minus x squared plus 6 as x goes to infinity. That's fine. Just multiply both sides of the previous twiddle by e to the minus x squared plus 6. Okay, so consider the new integral, just x to the 1,000 e to the minus x squared plus 6. And we're going to go from 10 to infinity. The intuition here is that although x to the 1,000 becomes huge, the exponential becomes really, really tiny. So I'm going to add 2 to 1,000, and I'm going to write e to the minus x squared plus 6 is less than or equal to some constant over x to the 1,002. And now this is less than the integral x to the 1,000 times the constant over 1,000, x to the 1,002. And again, the magic works. It's not really magic, but you end up with 1 over x squared, which converges by the p-test. Okay, so this new integral here is less than or equal to something which converges by the p-test. Therefore, the new integral, which I'll rewrite, converges by the comparison test. Right? It's less than or equal to something which converges. You can see it very clearly. This is finite. This is finite. This is even less. It's still finite. Everything's positive. Therefore, the original integral x to the 1,000 plus x squared plus sine x e to the minus x squared plus 6 dx converges by the limit comparison test. After all, this twiddles this. Right? It's exactly that whole line up there. So we've used the p-test, the comparison test, and the limit comparison test in order to do it. Because sometimes you have to use multiple tests. All right? A tricky example. As I said, it's not the only way to do it. There's definitely multiple ways, but to me it's probably the most intuitive, at least within this framework. The exponential's growing quickly. Any questions about that? Going to move on to logarithms. A question? Yeah. The question is, did I actually do the limit comparison test? I did. I know this converges, and I didn't use it yet, but I somehow want to make the leap from this one, which I know about, to this one, which has this extra garbage here, x squared plus sine x. So how did I make the leap from this to this? With the twiddle here, actually. Right? I could have done it by comparison if I was clever enough. The problem is, this one's actually bigger than this one. You really want this to be smaller than this if you're going to use comparison. So comparison doesn't work from this to this. You need to use the limit comparison in this case. So I did actually use the limit comparison test and the comparison test separately. All right, let's talk about logarithms. Yeah. Okay, logarithms are pretty much the opposite of exponentials. In fact, they are the inverse functions. So logs at infinity, here's what you need to know. Again, I'm going to use the fact that logarithms are smaller than any power of x. Logs grow slowly. And the form that you need to, or that you should learn this in, for our purposes, is also an inequality, and that is log x is less than or equal to some constant times x to the alpha. That's true for x bigger than 1, say, and any alpha greater than 0, and this time you get the most power out of this statement when alpha is quite small, even if alpha is small. So in the other case, the exponentials, picking a bigger power never hurt anyone. But for the case of logarithms, a smaller power is good. So here is an example. Suppose you want to consider the integral of log x over x to the... Actually, I'm going to change the one in the book slightly. So log x over x to the 1.01 dx. Now it's time to use a little bit of intuition. Suppose the log x was not there. This was just 1 over x to the 1.01. Would that converge or diverge? Converge. It would converge because the power 1.01 is bigger than 1. So the log x on the top, I mean, if this was x, imagine if instead of log x, I'll put it back in a second, imagine this was x to the 0.5 or something. If you cancel this out, you'll get 0.51. And this big thing on the top has made this smaller than 1 in power. And that's no good. That would diverge. So the question is, how much difference does it have to have the log x on the top? And the answer is not very much. But you have to be clever about it. You have to use this principle. Okay, so I want you to think about that. Log x is going to drag that power down, but not very much. Not very much. In fact, it doesn't really drag it down at all, in the sense that you can always, it drags it less than anything that you want. But you need to quantify this. What am I talking about? I need a number that is so small that when I subtract it away from 1.01, I am still bigger than 1. For example, let's take log x is less than or equal to constant x to the 0.007. Okay, I've always wanted to do that on camera. I don't know why. Okay, anyway, so you could pick any number here so that when you take it away from 1.01, you are still on the correct side of 1. Let's see what happens if we use this. This is less than or equal to the integral from 2 to infinity, constant x to the 0.007 over x to the 1.01. And when you cancel this down, the constant comes out of the integral. You are left with 1.003. It's still bigger than 1. So this integral converges. And if you follow it through, therefore, the original integral, everything's in the right direction, converges by comparison. Comparison test. I should have mentioned that this convergence is by the p-test as usual. Okay, again, the power, although it didn't have to be 007, 0.007, it could be any number less than 0.01 in this case. The problem is that it kind of kills a little bit of the advantage. You have to make sure it doesn't make it below 1. Otherwise, you will be in the whoop-de-doo case. You'll have a divergent integral. Even if you take 0.01, so that when you cancel it, you just get 1 over x. It still diverges, and you'd be in the whoop-de-doo case. It would be equal to infinity, and you'd know nothing about the original integral. So you have to be very subtle about the power and pick something small. Again, you can't walk into this exam saying, I'm always going to use 0.00001. Because then I will use 1.000000001 and thwart you, and you'll be screwed again. Okay, I know you didn't ask it this time, but yeah, I thought I'd put the words in your mouth. All right, so that's how you deal with logarithms. Are there any questions about that particular example? Well, what I'd like to do is show you 6 examples involving logs to show you what's going on here and the difficulties that you're up against. And any one of these would be fair game on this test that you have tomorrow. I don't know about other schools, but I think they're all reasonable. I'm going to change the power to 0.001 to be consistent with the book, but clearly you just pick an even greater number of zeros. So the first example is the one we've just seen, modified very slightly, x to the 1.001. So there, 007 wouldn't work. You'd have to go 0007, which is very secret indeed. Right, so you have log x over x to the 1.001. We already know how to do that. You just have to change the above argument slightly. However, here is a different permutation, which has a completely different solution. Suppose I stick the log x on the bottom. How would you deal with that? Now, the log x not there. Does it converge or diverge? Converges. The log x actually helps you because it's big. And when you put something big on the bottom, it becomes small. This is actually smaller than the original without the log x. And that's good. That means you can just do a comparison. Well, that's almost true. It's almost true. It's not quite true. What are we actually doing here? We want this to be less than this. If this is going to help us, what do we know about log x? The question is, why not just say 1 over x to the 1.001 log x is asymptotic to 1 over x to the 1.001 as x goes to infinity? Who thinks that's correct? Okay, who thinks that's incorrect? Who doesn't think? Wow. Most of you don't. Not only do you not know which one it is, but you actually don't even know if you're thinking. Dear, you've got a lot of work before this exam tomorrow. Okay, anyway, this is not true. If this were true, you could multiply by this and cancel it out, and you get log x. You could take reciprocals, and log x would be asymptotic to 1, which it's not. Log x does grow, and 1 does not. This cannot be true. Okay, so this is not true. You cannot use these sorts of methods. On the other hand, this method here is almost true. It's almost true. The only problem with it is that log x, when x is bigger than e, everything is fine. But we're going from 2 to infinity, so if I'm really going to do it properly, this is what I'd like. It's almost true. Let me show you how close we were to this. Log x, how small could log x be when x is between 2 and infinity? Well, log is increasing, so this is at least log of 2. So 1 over log x is less than or equal to 1 over log 2. So 1 over x to the 1.001 log x is less than or equal to 1 over log 2 times 1 over x to the 1.001. And so if you look at this, everything would be correct if only I threw in this constant 1 over log 2 out the front. So I want you to look at this. This is true when x is bigger than 2. This is very different from what we did in the previous example. In the previous example, we had log x is less than or equal to something. Here, we have log x is bigger than or equal to something, which is just some number, log 2, it's about 0.7. And the point is that we really need to take the reciprocals because the log is on the bottom. The log is on the bottom, so 1 over log x is less than or equal to 1 over log 2. Now you have less than or equal to, so this is less than or equal to, so you end up with this. And if you don't want to write that, you can just put some number c, which I may informally not call an ass-covering constant. If you don't put it in, it's not quite true. So you put it in to cover it. Well, anyway, so the point is that it doesn't really matter. You can always stick a constant out of anything like this, and it doesn't affect the answer. In this case, it's not quite true without the constant. This number is about 1 over 0.7. It's a little bit bigger than 1. And so this is true. Therefore, this converges by comparison again. So the gut feeling was that this time the log x helped us, and I just needed to ignore it, basically. Put the constant in, and if you really want to see what the constant should be, 1 over log 2 will do. So it's quite subtle. It's a different. It makes all the difference in the world whether the log x is on the top or the bottom. All right, so that is one type of variation, if you will. But there are more. Time is running away. I've got to move on. Luckily, there's no other functions that I want to look at. So I might start abbreviating some solutions. Anyway, I do want to deal with one other very important type here. Okay, suppose I do 1 over x log x. Now the intuition can be a little bit tricky. You see, 1 over x diverges. The integral diverges. Throw a log x, and it kind of helps it a little bit, because it makes the denominator bigger, which means the whole thing is smaller, so it has more chance to converge. Right? Something diverges. If I make it smaller, it might converge, if you're lucky. So does it? Well, the problem is this log x isn't quite even a whole power of x. If this was x to the 0.01, this would be x to the 1.01 when you combine them, and it would converge. The log x is somehow like a sliver of a power, x to the tiny, tiny something, but smaller than anything. It doesn't really exist. So does it help enough? I think of it like a scale. You know, x is there, and I'm putting a feather on it, a tiny little feather. Does it sort of change at that point? Well, who knows? Let's see. I can't use any of the inequalities. To do this, I have to use a substitution. Remember? Integrals can substitute. Watch this. Let t equal log x. Well, miraculously, dt is 1 over x. That's exactly what you have there, 1 over x dx. Also, when t equals 2, when x equals 2 rather, t equals log of 2. And as x goes to infinity, log infinity is infinity. Log also goes to infinity, more formally. And so this integral in t land becomes the integral from log 2 to infinity. 1 over x dx is dt. And then we have the log x on the bottom, which becomes a t. So, lo and behold, we now have reduced it to the p-test, but in t-land, the log 2 doesn't matter. It's the infinity that's the problem spot, and this diverges by the p-test.
Why didn't you just say what you told us? Assume that natural log of x adds just like x to the 0.000. Why can't you do that?
Well, suppose you said, oh, it adds 0.00001. Well, then, if that were actually true as we've stated it, then this would tip it to 1.000 and it should converge. But as we see, it diverges. The problem is, it doesn't actually add any power of x. It's in the cusp. It's in this void that we can't even imagine between the lowest power and just 1. So it's just a mental rule of thumb, but the problem is we can't tell how much it adds. On the basis of this, it doesn't actually add any positive power of x, because if it did, then it would tip it over to convergence. But it doesn't. On the other hand, let's suppose we put in a square of log x. So this was the next example I wanted to look at. And then I really have to move on to integrals at 0. So suppose I do log x squared. Well, the same substitution will lead us with dx over x is still dt, but I now have 1 over t squared, and that actually converges by the p-test. So if I have, in other words, if I have 1 over x times something, and if the something is 1, this diverges. So here's the scale. If I throw on a log x, it's closer to convergence, but it's still divergence. Log x is tiny compared to x. It's smaller than any power of x, really. Positive power of x, but still, it diverges. On the other hand, if I throw in yet another log x, it converges. So somehow log x is really very, very sensitive. It's like adding in a grain of microscopic dust, and it doesn't change the scale. And then you add in one other grain of microscopic dust, and all of a sudden the scale does that. Of course, if you put in any power of x, like x to the 0.001 in there, it also converges, because the total power will be bigger than 1. So this is the answer to your question. Why can't you just say, oh, log x is like a power? Because it's not. But if you want to get a sense of how big log x is, it's smaller than x to the 0.00000 for anything. That's all you can say. But it's bigger than 1. It's in this weird zone. All right. There's 3 more examples in this section, which is my reference. There's 3 examples of logs that you ought to take a look at. Well, it's in 21.3.4, I believe. So look at the other examples in 21.3.4. Make sure you can do them. That's my advice. I don't have time to do them now. All right. On the other hand, I do have to talk about behavior near 0. Yes, I've also missed some stuff about exponentials just because I don't have time. But the good news is that we've moved on to behavior near 0. So everything I've said has been about infinity. Now I'm turning my attention to problem spots near 0. So that's more like the vertical asymptote style. All right. So let's start off with polynomials. Here you go. You wanted to see polynomials. So 1, polynomials. How do they behave? Well, this time the lowest power dominates.
And also, not only when they go to 0, but when they go to some other number from both sides.
Okay, so let me do 0, as I've done infinity. Then I will tell you how to handle problem spots not at 0 or infinity. Okay, so let's just start at 0. Lowest power dominates near 0, i.e. p of x twiddles am x to the m, where this is the lowest degree term. And this is as x goes to 0. Why is that true? Well, let's look at an example and we'll get an idea. consider the integral from 0 to 5 dx over x squared plus root x. So what are the powers on the bottom here? You have x squared and you have x to the 1/2. So which one is more important at 0 or near 0? X to the 1/2. The lower power dominates there. So it is true that x squared plus root x twiddles root x, the lowest power. In fact, let me first write this as x squared plus x to the 1/2, which twiddles x to the 1/2 as x goes to 0. And in this case, we better put a plus because you cannot take the square root of a negative number. Okay, why is it true? Whenever you write something like that, you ought to justify it. And you do that by taking the limit as x goes to 0 plus of the ratio x squared plus x to the 1/2 over the lowest power, x to the 1/2. Well, if you simplify this, you get the limit as x goes to 0 from above of x to the 3/2 plus 1. Now plug in x equals 0. And this goes away and you just get 1. So to deal with this, you do a limit comparison test with, and you need to write out the details. I just don't have time to keep writing consider blah by the limit by the p-test. You do a limit comparison with just dx over x to the 1/2, which converges by the p-test. Now everything's opposite. When the problem spot is at 0, the p-test flips around and now numbers less than 1 are what you need to converge. So 1/2 is good. Okay? You could also do it by direct comparison with this, and that would work too. Simply because this quantity on the denominator is bigger than this, so the reciprocal is less, and everything does work the right way. But you don't even need to worry about it, whether it works or not, which way things go with limit comparison test. So I like that better when you have it. All right. Any questions about that example? It's a very interesting exercise in a way to compare just how different it is in a way and also how similar in another sense it is to the same integral, but when you're going from 5 to infinity. So let me just do that for 1 second. So if you have the same integral from 5 to infinity, dx over x squared plus root x, everything is different here. Now, x squared plus root x does not behave like the lowest power. It behaves like the highest power as x goes to infinity. Compare that with the other one. This behaves like root x as x goes to 0. But it behaves like x squared as x goes to infinity. So 1 over x squared plus root x twiddles 1 over x. And you use limit comparison with, again, you supply the details, just dx over x squared. Now the x squared term dominates. Again, you could use regular comparison because it works. You see this converges by the p-test. This time the problem spot's at infinity, so 2 is bigger than 1. That's good. A question in the front first, yeah. Well, in this case, there is no 0 problem spot. But what happens if you have this integral? I'm preempting, I'm sort of trying to develop your question a little bit by talking about what I was going to talk about, which is now you have 2 problem spots, one at 0 and one at infinity. You can never handle 2 problem spots in the same integral. You must split up the integral. Pick any number in between 0 and infinity. I might as well pick 5, but 5, of course, is irrelevant here. And you get the 2 integrals that we've just looked at. So you've split it up first. Now the only problem spot is at 0 and infinity, both integrals have only one problem spot, and we have to analyze them separately. So you would have to redo or duplicate all the work that we've just done in the two previous examples and conclude that they both converge. And if they both converge, so does the sum. Therefore, so both converge, both pieces converge, so does the original integral. What if one converges and one diverges, or indeed if both diverge, or anything like that? Well, then the whole thing diverges. If any piece diverges, the whole thing does. And you don't even have to bother checking any remaining pieces. If you had checked this and it happened to diverge, screw that one, doesn't matter. Okay, so another question.
What is the integral of dx over x squared plus the square root of x minus 5?
Okay, so the question...
From 3 to 7, and then from 5 to 7, and 5 to 6.
So you're worried about this, x squared plus root x minus 5. That's if I understand correctly. Now, the thing is, you want to go from 3 to 7, but forget that because x has to be at least 5 for this to even make sense. So the best I could do is from 5 to infinity. Now, if you split this up into two pieces, one might be from 5 to 7, say. And the other one might be from 7 to infinity. Although the number 7 is at your discretion. It just has to be bigger than 5. Now, this piece, you also have x squared being the dominant term. So this is as before. You can use limit comparison to see that it converges. Unfortunately, this piece, the problem spot is now at 5. And you are trying to force my hand to tell me something I'm going to tell you in half an hour. But I will tell you now, because you've asked me twice. And I need to get rid of this. If the problem spot is not at 0, you can transfer it to 0 by making a substitution. So in this case, I will set t equals x minus 5, so I can understand what's going on. If I do that, dt is the same as dx. dt is the same as dx. And therefore, this integral becomes, after the substitution, when x equals 5, t goes to 0. When x equals 7, t goes to 2. And dx is the same as dt. X is t plus 5. So you're going to have t plus 5 all squared plus root t. So in t land, that's what I get. Now the problem spot is actually this time at 0. Or is it? Is 0 even a problem spot? No. You plug in 0 and you get a perfectly good quantity on the bottom, which is around 25. So actually, this didn't even have an original problem spot, and in fact, we didn't even need to split up the integral into two pieces in the first place. So the only thing that would be interesting is if you allow me to change this problem here, let's take a hiatus and consider this problem. Suppose this was the actual problem. X minus 5 all squared plus root x minus 5. Now, there's a genuine bona fide problem spot at x equals 5, because now the denominator vanishes. But in t land, this would be 0 to 2 using the same substitution, t squared plus root t, which is the same problem as we just saw, and we use limit comparison test. I don't want to redo it. It's the same as the one on the previous blackboard there, 0 to 2 instead of 0 to 5. So question?
What if there were like a plus sign, but it was multiplied, x minus 5 whole square, multiplied root over x minus 5?
So you say this times this? Well, in the substitution, you get t squared times root t. And if you ever had t squared root t, you should write that as t to the 5 halves. And now that's bigger than 1, so it would diverge in that case. So you can handle all of these things with these principles. Okay? Another question?
Can it be done without substitution?
Yeah, but I mean, it's easier with substitution. Can it be done without substitution? Yes, but then you have to start saying x minus 5 twiddle something minus 5 as x goes to 5 instead. It's so much easier to just transfer everything to 0. I still have to tell you what to do if it's the upper end point, which I want to look at in a second, but I have a question up the back.
When you're solving this, do you ever actually have to take the integral
That's a good question. You notice that we've almost done no definite integrals. We just did that one with cosine. The fact is, often these things are so nasty that you can't, and that's why you have these tests. You turn nasty functions that you can't integrate into nicer ones. But I'll tell you what, if the tests don't look like they work out and you think you can find an antiderivative, by all means do it using a limit, such as the cosine x1. Okay, any other questions at the moment? I'm going to finish. I'm still sort of dealing with behavior near zero, but I'm going to have to finish my train of thought. I've showed you how to do a substitution for a left-hand problem spot that is not 0. You just substitute t equals x minus a, where a is the problem spot. But if it's on the right-hand side, then that substitution doesn't quite work. There's a slightly different substitution. And I will show you a quick example, and then I will return to what I was talking about. We've wasted no time because I was going to say this anyway. I've just changed the order in response to persistent questioning. So consider this integral. Actually, I might as well use the example that I was going to do. Actually, consider this example. What's a good example? Here. This is something that we actually, it came up last week. I had this integral that I broke up into 5 pieces. It doesn't matter if you weren't here or if you didn't see it. But just for completeness, I said I was going to look at some of these pieces. One of the pieces was this. So let's just consider it on its own merits. You have this improper integral. It looks a bit nasty. My question to you is, where is the problem spot or problem spots? Well, the denominator blows up at 0, 1, minus 1, and 2. Those are the bad ones. And the only thing that is in between 3/2 and 2 inclusive is at 2 itself. Our original integral that I wrote up last week was from 0 to 3, and then we had to split it up into 5 pieces. This is one of the pieces. So does it converge or diverge? Well, the problem spot is at 2, which is not 0. Also, it's at the right-hand endpoint, and everything I've showed you is on the left-hand endpoint. Well, never mind. Watch this trick. T, if it was from 2 to something, I'd let t be x minus 2, right? That would transfer the problem spot from 2 to 0. Well, now I let it be 2 minus x. Slightly different. I just take the negative. So what does this do? Well, dt equals minus dx. So that's a little bit different because there's a minus sign. But I'm going to use this to flip the bounds of the integral. So you might as well have taken a subheading. I've sort of jumped ahead to section 21.5. All of this is 21.5. How to deal with problem spots that are not at 0. We've already discussed how to do the left one. To do the right one, t equals 2 minus x, dt negative dx. Let's see what happens. By the way, we might as well write x equals 2 minus t. So this integral in t land, when x equals 3/2, t is 1/2. And when x equals 2, t is 0. And I have 1 over. X is 2 minus t. X minus 1 is 1 minus t. X plus 1 is 3 minus t. And x minus 2, well, is negative t. And this is dx is minus dt. So that's the substitution in this integral. Looks a bit nasty. Let's deal with it. I said use this minus sign to flip the bounds. So I'm going to ignore the minus sign. I'm going to get rid of it and go from 0 to 1/2 of this quantity. 1 over, well, it's, what is it? It's t. I'll put the minus, well, whatever. I'll keep it as it is. 2 minus t, 1 minus t, 3 minus t times minus t. It's a bit unfortunate that this quantity happens to be negative on the bottom, but never mind. In fact, I will pull out the minus out the front so that it's now, everything is positive. When t is between 0 and a half, all four of those factors are positive. Okay, so what happens? What happens? Well, the easiest way to deal with this, first of all, note that the problem spot is at 0 now. And it just comes from that t. Pretty neat, huh? I changed the problem spot at 2 to 1 at 0. And at the same time, the 2 on the right-hand endpoint became the 0 on the left-hand endpoint. Well, watch this. 2 minus t behaves like minus t. No, it doesn't. It behaves like 2 as t goes to 0. Do you believe it? When t goes to 0, this limit, 2 minus t, is actually equal to 2. So, of course, the ratio goes to 1. The lowest power, in this case, this is 2t to the 0. Lowest power dominates. So 2 minus t twiddles 2. 1 minus t twiddles 1. 3 minus t twiddles 3. So the product of these things, 2 minus t, 1 minus t, 3 minus t times t twiddles 6t. 2 times 1 times 3, 6t. So I'm going to use, on this integral, limit comparison test with the integral of dt over 6t from 0 to 1/2. Don't worry about the minus sign yet. That minus sign out the front, I'm just ignoring it for the moment. This diverges by the limit comparison test. So with the minus out the front, so original integral diverges to minus infinity. So that's actually one way to handle a negative, even though I said there wasn't. I was going to do it later. Later is rapidly becoming soon because I have a lot more to do. Quick question. T, 0 minus t. No, it doesn't make a difference. 0 minus t is the same as minus t. No, nothing ever twiddles 0. Nothing twiddles 0. You cannot say 0 twiddles 0 minus t twiddles 0. 0 is not a power of t. It's nothing. And nothing can ever twiddle 0 because you can't divide by 0. Quick question.
Yeah, so you have a negative integral twiddling another negative integral?
No, I don't really. Unfortunately, I wasn't very clear about this. I said ignore the negative for the moment. That integral twiddles this positive integral, and that diverges to infinity. Now the minus of it goes to minus infinity. Okay, sorry about that. I still have to tell you how to deal with negative, and I am rapidly running out of time. I still have half an hour, so please bear with me. I am going to move on to trig functions near 0. This is the most significant thing that I have left to say. Trig functions near 0. Okay. Here's the deal. We've got some new twiddles that are different from the other sorts that we've seen. Sin x twiddles x as x goes to 0. You believe it? Okay. Shh. Need my voice tonight. 4 hours. Not 4 hours of video, though. Sin x twiddles x as x goes to 0. Why? Because sin x over x goes to 1. Similarly, tan x behaves like x as x goes to 0. You can just quote these because these are known limits. On the other hand, cosine x does not twiddle x. It behaves like 1 as x goes to 0. After all, cosine of 0 is 1. So these you ought to be able to, you ought to remember them. They're really, really useful. So what example would I like to use? Here's one. Well, here's a simple one. Consider these two integrals. So the integral of 1 over tan x and 1 over root tan x from 0 to 1. The only problem spot in both integrals is at 0. Because tan 0 is 0. There's no other problem spots, as it turns out. So how are we going to deal with this? Well, tan x behaves like x as x goes to 0. So 1 over tan x behaves like 1 over x as x goes to 0. So this one, I'm going to use limit comparison test with the integral of just 1 over x. After all, 1 over tan x behaves like 1 over x at the problem spot. Does that diverge or converge? Diverges by the p-test. How about the other integral? Well, if we take square roots, we can see 1 over root tan x behaves now like 1 over root x as x goes to 0. And now, if we're going to be proper about it, we'll put a 0 plus. Again, you cannot take the square root of a negative number. So this one, you're going to use limit comparison test with 1 over root x, which is otherwise known as 1 over x to the 1/2. And this now converges by the p-test, because the power of 1/2 is less than 1. So that one converges. Limit comparison test. Again, both of them need more working. You need to fill it in, but I don't have time to do it. And it's a good exercise for you to do. Okay, a couple more examples before I dispense with trig functions. In fact, I'm going to have to skip exponentials and logarithms and just leave it for you to read so I get done. Those in the room, I'm doing another 2 hours because of the midterm tomorrow, just of problems that you might have, questions, so they might come up there, but they don't come up very often, at least not in these types of exams in my experience. Consider this integral. Sine x over x to the 3/2. This is very similar to one we did earlier, sine x over x squared. Okay, integral sine x over x to the 3/2. The problem spot is at 0 again. That's the only problem spot. So how do I deal with this? Sine x behaves like x as x goes to 0. Sine of small looks like the same small. So now divide by x to the 3/2. And that twiddles x over x to the 3/2, otherwise known as 1 over x to the 1/2. As x goes to 0, again, I better take 0 plus because I'm taking square roots. So this one can be solved by limit comparison test with the integral from 0 to 1 of 1 over x to the 1/2, which converges by the p-test. So the original one converges. Again, more work is needed, but that is the guts of the proof. Any questions about that one? Question, yeah.
What is the justification for being able to divide by x to the 3/2? Doesn't that require some more justification to divide by?
Suppose that you know that f of x twiddles g of x as x goes to a. I claim you can divide that by anything you want as long as it's non-zero. Okay, why? Because you're looking at the limit of the ratio f of g, and you're saying that's equal to 1. But this is also true if you replace this by, say, f of x over x to the 3/2 divided by g of x over x to the 3/2. After all, they just cancel out. So that's why you can multiply by the same quantity, because the asymptotic means that the ratio is near 1. And if you have the same thing on both sides, it just goes away. Right. So, now, what else do I have? I have one other thing. Just because I have told you that this is a problem spot at 0, well, I haven't really said that. I've said behavior at 0. There are cases where the problem spot is at infinity, and yet it's really a behavior at 0. Consider this. Here's a nasty trick. integral from 0, let's go from 1 to infinity actually, of sine 1 over x. Is this the example I want to do? Sure. Now you might look at this and say, oh, I know how to do this. Trig functions when x equals large. Remember, I did that much earlier. I said, oh, you've got to use sandwich principle. But the thing is, the problem spot's at infinity, and 1 over a huge number is small. So actually, the real critical thing is what happens to sine of a small number. Watch this. Sine x behaves like x as x goes to infinity. But you can replace x by something else as long as you replace it everywhere. Sine 1 over x behaves like 1 over x as 1 over x goes to infinity. I'm sorry, this is as x goes to 0. I'm ahead of myself. As 1 over x goes to 0. Thank you. Let's start again. Sine x behaves like x as x goes to 0. Therefore, sine 1 over x behaves like 1 over x as 1 over x goes to 0. And that will happen as x goes to infinity. Or minus infinity. So, for the limit comparison test, you use 1 over x, which diverges by the p-test. Again, the full solution, I've actually written it out in some more detail in section 21.4.2 of my book. So, that is an example where the problem spot at infinity still needs the technique at 0. And the reason is because you have a 1 over x before you take the sign. The same would be true for any sort of function of 1 over x. You really are transferring a problem spot at 0 over to infinity by the reciprocal. So it's pretty tricky stuff. All right, so look, I said I wasn't going to say much about exponentials or logs. Basically, exponentials don't do anything special near 0. E to the x behaves like 1 as x goes to 0. It's just like a cosine x. It's almost not even worth saying this. You know, e to the x behaves like 1. The fact is, if I took any of the previous examples, let's say, take this example, we saw that this one converges. We saw this converges just on this board over here. What if the problem was just e to the x over root tan x? Well, the previous solution said 1 over root tan x behaves like 1 over root x. That's what we did before, at least as x goes to 0 plus. Now we have an e to the x, but e to the x behaves like 1. So maybe I'm being a little bit presumptuous. Take this relation and this relation, and you can multiply them together to see that e to the x over root tan x behaves like 1 over root tan x. 1 over root x, rather. So the same solution applies with a slightly different thing. And if you don't believe me, you can test this out by dividing and taking limits. Right? It's sort of along the lines. So that's a very technical sort of example. Log x, you know, I don't really even have much time to discuss that, but as I say, it's not really, I haven't seen it come up in Math 104 exams, and I'm running short on time. I have 15 minutes left. I have told you how to deal with problem spots not at 0. That was embedded before. What I have not told you is how to deal with functions which become negative. So I need the last 15 minutes to deal with that wrinkle, because you cannot use the comparison test or the limit comparison test. So what if your function is negative? There are 3 possibilities. What if the function is negative? Well, one possibility is that maybe the function is always negative. An example would be, and we'll scroll back over to this thing in T-land over here, that bottom integral there on the right. I pulled out the minus, But with the minus embedded in the thing, the integral is always negative. Well, if f is always negative, you can pull out a minus and write it as minus an integral that is positive. So in this case, write your integral as minus f of x. Now, this is always positive, right? F is negative, so minus f is positive. So if you've done this, then you can analyze this integral, minus f of x. And there's two possibilities. If it converges, then, hell, I mean, you put a minus sign, it still converges. It just converges to the negative of whatever this. So if this equals 3, then this is minus 3 in the limit. On the other hand, if this diverges to plus infinity, such as in our previous example, then this diverges to minus infinity. So basically, this does the same. If this converges, so does that. If that diverges, so does that. So if f is always negative, then that's the case. By the way, this integral here falls into that category, although I'm not going to do it because I can't deal with logs at 0. I don't have time. Read it in the book. However, log x is actually a negative function between 0 and 1. Log x looks like this. So log x is negative. I'm telling you should consider this as the integral of minus log x. But I'm not telling you how to do it, unfortunately. I'm just telling you how to get started. A better example in that context is the one that we've already done on this previous board, where I pulled it out. I got something that diverges to infinity, so the original integral goes to minus infinity, but it still diverges. So that's the one possibility. If the function is always negative, pull out a minus sign and make it always positive, and you can use our previous technology. Now, the interesting question is, what happens if the integral is sometimes negative and sometimes positive? And to do this, we need another test that I haven't mentioned yet, and it's called the absolute convergence test. And here's what it says. So, step 2, if f is sometimes positive and sometimes negative, try this test. Absolute convergence test. Here's what it says. So you have some integral here, where f of x is positive sometimes, negative sometimes. Again, either of these could be infinity, minus infinity, all that sort of stuff. What does it say? Well, consider instead the integral with the absolute value. Well, this is now positive. So you can use comparison, limit comparison. You've got all the tools available. So this is positive. If this converges, so does the original integral. That's what the test says. If the new integral converges, then so does the original one. However, if the new integral diverges, you don't know anything. It doesn't tell you anything. In particular, the absolute convergence test can never be used to show something diverges. So if you ever write this integral diverges by the absolute convergence test, you will probably get 0 for the problem. Or even negative points if we're sufficiently outraged. Okay, I don't think you get negative points, but anyway, You should. Okay, so the absolute convergence test can never be used to show something diverges, only converges. So here is an example. Suppose you have this integral sine x over x squared dx from 1 to infinity. The problem spots at infinity. It's very similar to one we looked at about an hour ago, where we had absolute values there. But it is not the same. It is wrong to use comparison or limit comparison on this, because sine x oscillates between positive and negative, and you cannot use the comparison test or limit comparison test in that case. Now, let's see what happens. In order to deal with this, I would say consider, and I notice that there are positives and negatives. All right. I take the absolute value, sine x over x squared. Now in this case, the denominator is always positive, and I've reduced it to the integral we had before, which, to remind you, we dealt with this using the comparison test very straightforwardly by using that. I'm not even going to go over it again. So this here converges by the comparison test. So the original integral, in its full positive and negative glory, converges by the absolute convergence test. Right, so to review, what's going on here is we started off with an icky integral that is both positive and negative. We said, I don't like it, took absolute values instead. Just forget about the original, take a new one, show it converged, and then the original one converges, but you quote the absolute convergence test. If we had found that this integral had diverged, we'd be in trouble. We couldn't use the test. There would be no useful information. Okay? So if the function is sometimes positive and sometimes negative, take the absolute value to make it always positive. See if it converges. That's what you'd like. If it does, so does the original integral. Now I spoke of one more possibility. You know what? This is going to take such a short time to do the third possibility, because I've already done it, that I could tell you about logs after all, and I probably should, just in case. I still have about 8 minutes. What the hey? I'm going to give myself 2 boards. So let's see. The third possibility is what happens if the absolute convergence test doesn't work. And then you're in really hairy territory, which approaches my PhD thesis sort of style. If absolute convergence test doesn't work, trouble. And you may have to use the definition of the integral. So an example of this is this one I looked at earlier. So I'm not going to redo it. That actually diverged in a different way. It was oscillating. Let's suppose we had tried to use the absolute convergence test. If we had tried to use the absolute convergence test, we would find that this integral is cosine looks like this. Actually, that's sine. I'll convert it into cosine by starting there instead. Cosine looks like this. So the absolute value kills off the bottom, and it becomes like waves. Well, it was already wavy, but... So we're asking, what's the area of this? And so on. Each of these waves is identical, and they're all 2, as it turns out. So 2 plus 2 plus 2 plus 2 plus 2. This is infinity. So actually, you cannot use the absolute convergence test. You learn nothing about this integral. Instead, you have to do what we did before, which was to write this as the limit as n goes to infinity, but since of the same thing. But since we already did that, I'm not going to do it again. All right. So just a couple more minutes. Any questions about that? I'm hitting you with a lot of stuff. It's a big topic. There wasn't much time for it. That's life. Let me just quickly jump back and tell you the one thing that I really should have said that I didn't get a chance to say. Log x near 0. I really should give a reference for this since I'm jumping around. What is the reference? The reference is not even on that page. 21.4.4, I think. It's very similar to log x near infinity, but when x is between 0 and 1, log x is actually negative. So this is positive. And the point is that there is an inequality that is similar to the one we looked at before. But this time the x to the alpha is on the bottom. It's just another fact. It has a reason. Absolute value of log x looks like this. At least from 0 to 1. But it doesn't grow as fast as 1 over x or even 1 over root x or anything like that. So for example, to do this integral, just log x, absolute value, I would just say pick a power less than 1. So I'm going to take absolute value of log x is less than or equal to some constant over x to the 1/2. I get to pick any power there, and I want to pick a small power. I'm going to pick 1/2 because it works. It's small enough so that the p-test says this converges. So this integral converges by comparison. So this integral is less than or equal to this integral. I've left out the constant. Well, the constant can come out the front. And there is how I would do the integral of log x. Things get a little bit nastier when you have powers in the denominator here, and there's a complete survey in this section of the book. But this would be the most sort of easy question of this sort. Let me just comment that if you had to do the integral of log x without the absolute value, I would first write that as minus the integral of minus log x. After all, log x is negative between 0 and 1. And this is, of course, the same as absolute value of log x. Well, we've seen that this integral converges to some positive number. So this with the negative converges to some negative number. And the picture of the situation, which is what I'm going to finish off with, looks like this. I want to find log x between 0 and 1. This area, is it finite or is it infinite? Well, whatever it is, it's negative. It's either negative infinity or it's negative some number. So I take the absolute value instead, which is the same as the minus, and I analyze this case using that inequality, and I find that that area is some finite number. It converged. Therefore, this area is just the negative of it, but it's still a finite number. All right, so that is some sort of survey of improper integral problem solving. Most of what I've done is just techniques for solving these problems. It's not going to cover every technique, every type of problem, but gee, that should cover a lot of them. So now you have to practice a lot by tomorrow, if you're in the room. Otherwise, hopefully you have a little more time. Anyway, next time, which for those in the room is going to be in 2 weeks, we are going to do sequences and series. So until then.